We are live now.
Okay. Welcome everybody to the STCS seminar. Thanks for coming at a non-standard time. We are delighted to have Girish, a graduate student from Princeton, to give a talk today. Girish is a friend, I can possibly say an alumni of TIFR. She spent a good year and a half out at TIFR. And before moving to Princeton, she's been working on several areas related to Fourier analysis and more recently on parallel repetition. She'll be speaking on parallel repetition for the GHZ game, a simplified proof. Floor is yours.
Thanks, Prahlad. Yeah, thanks for the invitation. I'm very happy to be talking at TIFR again. I'll be telling you about a simplified proof for the parallel repetition for the GHZ game. This is a joint work with Justin, Kunal, Ran, and Wei. I'll begin by telling you our results quickly, and then I'll go on to introduce the background for our results. So feel free to interrupt me with questions if you have. Okay, so here is our result. We give a new proof that the value of the n-fold parallel repetition of the GHZ game is at most inverse polynomial in n. So we show that the parallel repetition of the GHZ game reduces the value polynomially quickly. This was first shown by Justin and Ran last year. We give a new proof of this fact, which we believe to be much simpler and more direct. Now let me describe what all these terms mean. Let's start with multiplayer games. So what is a multiplayer game? There is a verifier and there are k players. There is some distribution mu and there is some predicate v. These are known to everybody. The verifier samples an input x1 up to xk from mu and sends the ith part to the ith player. So for example, player I receives xi and replies with yi. There is no communication between the players. So the only thing the players can see is the input they receive. So their answer must depend only on this. So yi is a function of xi only. We say that the game is 1 if the predicate on x1 to xk and y1 to yk evaluates to 1. So if this predicate equals 1, we say that the game is 1 on input x. If it's 0, we say that the game is lost on input x. We say that value of g is the maximum probability of winning this game. So by maximum, we mean maximum over player strategies. By strategy, we just mean a function that maps xi to yi, basically what the player should reply when they get a certain input. And the probability here is taken over inputs drawn from this distribution mu. So these are multiplayer games. Just to emphasize here, everyone knows mu and v. This is known to all the players. And also the player strategies are known to everyone. The players can agree to play according to a fixed strategy. What is unknown here is the exact input that the players receive. Only the verifier and player I know xi and yi. So this is a multiplayer game. Any questions? Let's look at an example.
Yes, I was just saying that here we can assume that the strategy does not involve randomization, right? Because I guess that does not really help.
Yeah, that's a good point. So you can imagine a strategy which allows the players to sample some private or even public randomness and then decide what y should be. But we can just fix a strategy that maximizes this. So by linearity of expectation, you can just assume that the strategies are deterministic. So we're going to assume that. Okay, so let's look at an example. So let's look at the GHZ game. Here, the verifier samples an input x, y, z uniformly at random from 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0. So you can think of these 4 points as the hyperplane over f2 cube. This hyperplane is defined by x, y, z such that x plus y plus z is 0 mod 2. I'll often refer to this as the GHZ distribution, the uniform distribution on these 4 points. Now, the verifier, there are 3 players. The verifier sends x to Alice, y to Bob, and z to Charlie. Alice, Bob, and Charlie reply with bits A, B, C, and they win if this property is satisfied. X or Y or Z equals A, X or B, X or C. This is the GHZ game. So one strategy that the players could do is to always return 1 regardless of what they received. So in this case, this quantity here is 1. And you can see that the players win on all inputs except 0, 0, 0. So this is a strategy that wins with probability 3/4. And you can actually show that this is optimal. That is, every strategy is going to fail with probability at least 1/4. So this is an example of a game with 3 players whose value is 3/4. Now let me introduce parallel repetition. So in the n-fold parallel repetition of a game, the players are given n independent instances of the game, and they need to solve all these instances simultaneously. So for each I from 1 to n, the verifier samples independently from the distribution mu and sends the ith part of all instances to player I. So for example, player 1 gets x11 up till x1n, and the player replies for all these instances, so replies with y11 up till y1n. So notice that y11 can now depend on all the inputs that he or she received. And their goal is to win all the instances. So we want the predicate to evaluate 1 for all I from 1 to n. And the value of g to the n is, as before, the maximum probability of winning all the instances. So the maximum is now over strategies for the n-fold game. So by a strategy for the n-fold game, we mean a function that maps these n inputs to these n outputs. And the probability is over inputs drawn from mu to the n, which is n independent copies of mu. So this is the n-fold parallel repetition of G. And the question here is, what is the asymptotic behavior of value of G to the n as n goes to infinity? This is a very natural question to ask. You have a multiplayer game and you want to reduce the value of the game. The natural thing to do is to have several copies of the game and run it in parallel. And the question is, how does this decrease the value of the game? So this is a really basic question, and it has very close connections to PCPs and hardness of approximation. It also has other applications to geometry of forms, quantum information, communication complexity, and so on. This is for 2-player games. For 3-player games, it was recently shown by Kunal and Ran that strong parallel repetition for a certain class of games implies superlinear bounds on non-uniform Turing machines. This was something that's not known. And there's a general intuition in the field that the kind of bottlenecks you encounter when trying to prove multiplayer parallel repetition is similar to the kind of bottlenecks you encounter when trying to prove direct sum and product theorems in number on 4-head communication complexity. So it's natural to hope that techniques here might extend to techniques there. So these are the various motivations for studying the parallel repetition question. What do we know about this question? So you can show that value of g to the n is at least value of g to the power n, because whatever strategy the players had for the initial game, they can just use the same strategy for all copies of the game. Each copy is one with probability value of g, and the n copies are independent. So this shows that value of g to the n is at least value of g to the power n. One might hope that value of g to the n is at most value of g to the power n, but this is not the case. There exist games for which value of g to the n is significantly larger than value of g to the power n. So this is because the questions are given in parallel. So if the questions were given sequentially and the players had to answer sequentially, then there is really nothing better we can do. But because the questions are given in parallel, the players get to see a bunch of questions together. So they can use their knowledge of these questions to correlate their answers across the different instances. So now the games across different instances are no longer independent because the players have introduced correlation through their answers. So this inequality doesn't hold. But what do we know? For two-player games, it was shown that as long as the value is less than 1, it actually decreases exponentially. So this was first shown by Raz and later simplified and strengthened by Holmgren. We now know tighter bounds depending on the value of the original game. So for two-player games, we have a good understanding of the situation. But for three-player or more player games, we don't have a very good understanding. So the best bound we have is that value of g to the n is at most 1 over alpha n. Here, alpha n is the inverse Ackermann function. So this is something that goes to 0, but extremely slowly. So all this says is practically that the value of g to the n goes to 0 as you repeat it.
Hi, Uma. This is Arkadev.
Hi, Arkadev.
Yeah. So when you say this inverse, so this is for a general game, right? I mean, for specific games, we might have.
Exactly.
Oh, yeah. The next line itself.
The next line, yeah, exactly. Yeah, so this is for all general games, and this is a very general combinatorial argument that uses Hale's duet. But for specific types of games, you can do better. In particular, for expanding games, so this was shown by Dinur, Harsha, Venkat, and Yuen. They showed that for a class of games which they call expanding games, you can actually show exponential decay. So let's take a closer look at this result. So I'm going to present a simplification of the result, which is that so so under the assumption that G is a connected game, the value decreases exponentially fast. So let me tell you what a connected game is. So a connected game essentially corresponds to the fact that the graph on player inputs is connected. So what is this graph on player inputs? The vertices of this graph are all possible inputs to the game. So this is support of mu. And you connect two inputs x and x prime if they agree on the questions to all but one player. So you put an edge between x and x prime if they differ on exactly one of the k coordinates. And we say that the game is connected if this graph is connected. So what Dinur, Harsha, Venkat, and Yuen show is that for such games, you can prove exponential decay. They actually obtained tighter quantitative bounds depending on the spectral expansion of G. But for us, this is the main takeaway. So one can ask, what about other games? What about disconnected games? So in this work, they highlight the GHZ game. This is a highly disconnected game. And they suspect that understanding the parallel repetition value of this question is going to help understand the parallel repetition value of general games. So this GHZ game is an example of a game where the current techniques fail. So it's natural that this is the first step. Understanding the GHZ game is the first step to understanding parallel repetition for all multiplayer games. So let's recall the GHZ game. So in this game, a verifier samples an input x, y, z uniformly at random from these 4 points, 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0, sends x to Alice, y to Bob, and z to Charlie. And the players win if the answers a plus b plus c, the XOR of these answers is equal to the, it should be or, x or y or z. So this is the GHZ game. You can see that the input graph that I described before is highly disconnected. In the sense, to go from any one input to the other input, you need to change at least 2 coordinates. So here is an example of a graph that's disconnected. And the question is, what can we show? What can we say about parallel repetition for these kind of graphs? So in this sense, the GHZ game is interesting because it is where current techniques had failed. There's another reason why this game in particular is interesting. It's because it's very interesting from the perspective of quantum information theory. So it turns out that quantum strategies can actually get value 1. If the players are allowed to share entanglement, then they can actually achieve value 1. And this is also robust in the sense that if the players achieve value 1, then they must use a particular type of entanglement. So this game can be used as a test to check whether the players share this particular type of entanglement. But for us, we're going to be focusing only on the classical picture, and we're going to ask what is the classical parallel repetition value of this game.
Sorry, one stupid question here.
Yes.
Suppose I have a quantum strategy which is more than 3/4 but less than 1.
Mm-hmm.
Does it therefore give you some sort of a measure of the degree of entanglement used by the players? Or
Yes, I think this is like pretty robust in the sense like anything that gets close to 1 must have something like the particular. It is robust, yes. Does it answer the question?
no, okay, yeah, okay, we can take this up later. Don't worry.
Yeah.
It's also this, though you mentioned quantum, there's also this XOR repetition for which this is a very interesting. No? Do I make sense by you follow what I mean by XOR repetition, or? Hello?
Yeah, so I'm not sure.
No. So what I mean is, so parallel repetition is you repeat you send in n copies of the questions and the prover sends in n copies of the n answers. Mm-hmm. Now, because this particular game, the predicate is an XOR. The XOR is A XOR B XOR C. Suppose the prover, the verifier only wanted to check that the XOR of all the answers is correct. So each of the players don't need to send all the answers. They can just send the XOR of the n answers. And then the prover just checks. This is called XOR repetition. So the answer size remains just 1 bit each. Answer size doesn't grow n. And the general belief is XOR repetition will also go down to, will go to half the XOR value, is the parallel repetition. But the GHZ game is a game in which the XOR repetition actually doesn't go to half. It's bounded away from half. There is a strategy which keeps it bounded away from half.
I see.
Yeah, so most proofs of parallel repetition also prove XOR repetition. If you show parallel repetition goes 0, they also prove XOR repetition goes to half. But GHZ game is a game for which we know the XOR repetition actually is bounded away. And the reason is because you can use the quantum value of the game to round it and use Cyrilson bound to actually keep it away from half.
I see. That's interesting.
You don't have to talk about quantum. You can even in the classical world, there's something weird happening with GHZ game for repetition. Yeah.
I see.
Anyway, so
yeah, that's interesting. Yeah, I see. Yeah. Any other questions? I think there is a question in the chat that randomized strategy doesn't help. Yeah, in general, randomized strategy doesn't help. So you can actually show that if you have any game and a Z for that game, you can actually fix the randomness and get a deterministic strategy that gets the same value. So yeah, also the graph has no edges in GHZ. That's correct. The graph is completely disconnected. Yes. Okay, so now I'm ready to state our results again. So we show that for the GHZ game, the value of g to the n is at most inverse polynomial in n. This was first shown by Justin and Ron last year, and we present a new proof of this theorem, and which we believe to be simpler and more direct. So this is our result. 2 remarks are in order. So first, we don't really require the fact that it's a GHZ game. So any game, as long as the value is less than 1, would work. And secondly, the query distribution doesn't need to be exactly the GHZ distribution. Anything with the same support would also work in our theorem. So this is also true for the previous work. Secondly, unlike most proofs of parallel repetition theorem, we make no use of information theory. So the previous proof by Justin and Ron made use of information theory and Fourier analysis, but we are going to use only Fourier analysis and no information theory. So this is what I had to say about our results. I will move on to the proof now, but any questions about our results?
Okay, just you'll possibly talk about it at the end. You believe that it should be inverse polynomial, or do you believe actually it's actually inverse exponential and we don't know?
I think it would be a very interesting counterexample if for some reason you can do inverse polynomial, but we think it should be like inverse exponential. We don't, like, our technique has a bottleneck of inverse polynomial, but we don't think it should really be the case, or it would make a very interesting counterexample.
So, by the way, how does so you're bound? This is for the 3-player game or for general K-player game?
So this is for just the GHZ game for 3 players, but I mean, you can think of a variant of the GHZ game for K players, and I think you should just follow either by same techniques or even by embedding the GHZ game into it or something. So
no, but for how large a K?
Oh, you're asking if K. I think
can your techniques handle like K? Because on the number on the four-head model, typically with K equals log n, all sorts of crazy things start happening. So I'm just curious, do these things work for, say, K larger than log n?
What do you mean by that? I mean, as you repeat, more and more players start joining?
No, the original.
Oh, that's right. That's right. That's a good. What do I? Yeah, that's a good question. Sorry. Yeah.
Yeah, I'm not sure, but I feel like
no. I'm not sure about now my question. Thanks to Jayakumar's pointing out. Yeah. Never mind.
Yeah, so but I still feel like something like any GHZ like distribution, it should work. But yeah, I'm not sure exactly. There is a question in the chat. Yeah, it does not have to be an XOR game. That's right. Any game on the same distribution on these 4 points with the value less than 1.
Actually, sorry, just to point out one thing. I hope I'm not taking too much time. Yeah.
No.
So I think it can still be made sense of. More players join in the sense that I have a certain n in mind, and then I can allow sort of log n many players. The repetition is n times, and I have log n many players, and then I sort of try to understand the value of the game as a function of n.
Or maybe saying it slightly differently is like, if you have a game with n players and the goal is to reduce the value to inverse polynomial in n, how many repetitions would we need? That's probably that's an equivalent way of phrasing what Affiliation is asking, right?
Yeah, off the top of my head, I think anything that is GHZ like, I feel it should work, but I am not sure. I've not worked it out. So let's maybe think about this after the talk. Okay, so if there are no more questions about the result, then let's go on to the proof. So, okay, so I'll start by describing some notation here. Bear with me. So, okay, so now let's look at the n-fold repetition of the GHZ game. The inputs are drawn from this distribution P, which is basically the n-fold GHZ distribution. So it's x, y, z, which are now vectors each of which are vectors in f2 to the n, and such that their sum x plus y plus z is 0. So I'm going to call this distribution P. Let gamma be any distribution over inputs to the n-fold GHZ game. So this is any distribution whose support is contained in the support of P. We say that a coordinate J is hard for this distribution if the probability of winning the jth coordinate under this distribution is at most 0.99. So when you sample inputs according to gamma, the probability of winning the jth coordinate is at most 0.99. By standard arguments in parallel repetition literature, it suffices to prove the following claim. So it suffices to show that for any product event E, which is a product event across the players, so E1 is now a subset of Alice's inputs, E2 is a subset of Bob's inputs, and E3 is a subset of Charlie's inputs. For any such event E, whose measure is not too small. So the measure of E under the GHZ distribution, under the n-fold GHZ distribution, is at least inverse polynomial. For any such event, at least one coordinate is hard for P conditioned on E. So our original goal was to show that for the distribution P, solving all the n instances is hard. Now we need to show that solving some instance is hard, but for the distribution P conditioned on E, where E is a product event across the players with not too small measure. So we've reduced the problem from showing that all coordinates are hard to showing that some coordinate is hard for the distribution P conditioned on E.
What so that U1, E2, E3 here, just it's an arbitrary decomposition as a product event? Or?
Could you say that again?
So what are the EIs here? Are you saying E has an arbitrary decomposition as a product event, or?
Yeah. So E1, E2, E3 could be arbitrary subsets of the three players' inputs. And we want to show that for all such events, this is true.
So just to clarify, so for example, E2 is an event only on player 2's input, right?
Yes.
Yeah, okay.
Does that answer your question?
Yes.
Okay. Yeah, so in general, when you want to prove that the probability of winning n coordinates is hard, you would say, let's show that the probability of winning the ith coordinate is hard. The probability of winning the ith coordinate is small, conditioned on winning all the first I-1 coordinates. But the event of winning the first I-1 coordinates is not really a product event across all the players because it depends on the answers that all of them give. And the general idea is to condition on the questions and answers to the first I-1 coordinates. Now it becomes a product event, and the idea is that you don't reduce the measure by much. So the idea is it suffices to understand the probability of winning a coordinate conditioned on product events. So that's some intuition. It is all right if you did not follow the how to reduce it to product events, but for now, we're just going to assume that it suffices to prove this claim, and I'm going to now show you how to prove this claim. Okay, so here is what we want to prove. So here is a high-level overview of how we are going to do the proof. The first step is going to be to introduce a class of simple distributions for which we can exactly pinpoint which coordinates are hard. This is going to be a Bowtie distribution, which I'll define next. We're going to then approximate P conditioned on E by a convex combination of simple distributions. This is the difficult step. And finally, we're going to show that most of the simple distributions that appear in this convex combination are actually hard on a typical coordinate or are hard on a significant fraction of coordinates. This would imply that a typical coordinate is hard for each of these distributions, and therefore a typical coordinate is hard for P conditioned on E. So this is the high-level overview.
So you're saying this significant fraction of coordinates depends on the I, or I mean, for all I, it's hard for a single set of coordinates, or these sets are different for each I?
They could be different. That's the point. So for different Bowties, you could get a different fraction of coordinates. But on average, there should be one coordinate that's hard for many of them. Some kind of, yeah. So as long as each of them is hard on a good fraction of them, there will be one coordinate which is hard for a good fraction of the Bowties. And that would imply that the value of P conditioned on E on that coordinate cannot be close to 1. So yeah, we will look at this a little more formally, but okay, any questions about the high level overview?
Uma, can you just go to the previous slide?
Mm-hmm.
So this slide, the claim implies the val G.
Mm-hmm.
This had nothing to do with inverse polynomial. You could replace the n to the minus omega 1 with some p, and this will just be some p to the some order 1. No?
Exactly.
So this is n to the inverse polynomial comes more when you can prove this claim.
Exactly.
Okay.
Yes.
Okay. Okay.
So if only we could prove this claim with exponential here, exponential in n here, minus n here, then we'd prove exponential decay for GHZ.
Okay.
Okay, so let's look at the proof of this. So let me start by describing the simple distributions. So to describe these simple distributions or Bowtie distributions, we're going to consider a graph. This graph is different from the graph I described before. This is the graph of inputs to the players in the n-fold game. So you have a complete bipartite graph on 2 to the n by 2 to the n vertices. On the left, you have the set of all possible Alice's inputs to the n-fold game. So this is all n-bit strings. On the right, you have the set of all n-bit strings that are inputs to Bob. And you put an edge between every pair of inputs. Note that the edges of this graph are in one-to-one correspondence to inputs to all players in the n-fold GHZ game. So if you take an edge x, y, x is Alice's input and y is Bob's input, then you can look at x plus y. So let's just label this edge by x plus y. You can look at the input x, y, x plus y. This is going to be a valid input to the n-fold GHZ game. Conversely, given any input to the n-fold GHZ game, it must look like x, y, x plus y. And corresponding to that input, you have the edge x, y. So the edges in this graph are in one-to-one correspondence with inputs to the players in the n-fold GHZ game. So now that we're labeling this edge x, y by x plus y, each input z Charlie defines a perfect matching in this graph. So for every x on the left-hand side, you match it to x plus z. So every input to Charlie defines a perfect matching in this graph. For different values of z, you get different perfect matchings. And when you combine two different matchings, what you get is a Bowtie. So what is a Bowtie? It's basically 4 edges that look like this. You have a complete 2 by 2 bipartite graph. 2 of the edges come from some matching and the other 2 edges come from some other matching. So this is a Bowtie. More formally, we say that x0, the edges x0, y0, x0, y1, x1, y0, and x1, y1. We say that these 4 edges form a Bowtie if x0 plus y0 equals x1 plus y1. Equivalently, x0 plus y1 equals x1 plus y0. So these are equivalent in the sense, if you have this, you can just add y0 and y1 on both sides to derive this, and vice versa. So this is a Bowtie. We will sometimes think of Bowtie as a collection of 4 edges. We will sometimes think of it as a collection of 4 inputs to the n-fold GHZ game. So remember that each edge x0, y0 corresponds to some input x0, y0, z0, where z0 is x0 plus y0. So we'll sometimes think of Bowties as a collection of edges, sometimes as a collection of inputs. And by the Bowtie distribution, we mean the uniform distribution on the 4 elements of the Bowtie. So it could be the uniform distribution on these 4 edges, or it could mean the uniform distribution on these 4 inputs to the n-fold GHZ game. So this is a really important definition that we introduce. Any questions about what is a Bowtie? This is going to be really important for us. Okay, so already it's starting to look a little like the GHZ distribution. In the sense, a verifier samples XYZ uniformly at random from these 4 points from the Bowtie distribution, basically, and sends X to Alice, Y to Bob, and Z to Charlie. So Alice is going to get either X0 or X1, Bob is going to get Y0 or Y1, Charlie is going to get Z0 or Z1, conditioned on the tuple XYZ being one of these 4 points. So if you look at the indices, already you have the GHZ distribution here. So you can actually make this more formal. So here is the claim. If you have a Bowtie such that X0 and X1 differ in the ith coordinate, then you can embed the GHZ distribution into the ith coordinate of the Bowtie distribution. So if you look at the Bowtie distribution and you look at the ith coordinate, it's going to look exactly like the GHZ distribution. So pictorially, you can depict the 4 points in the Bowtie distribution by this. So you have X0, Y0, Z0, X0, Y1, Z1, X1, Y1, Z1, and X1, Y1, Z0. And the claim is that if you look at the ith coordinate, it's going to look exactly like this. You have 0, 0, 0, 0, 1, 1, 1, 0, 1, and 1, 1, 0. The proof of this is quite simple. So we're assuming that X0i is different from X1i. So together they must be 0 and 1. We can assume that X0i is 0 and X1i is 1 without loss of generality, because you can just swap these roles of X0 and X1. Similarly, you can swap the roles of Y0 and Y1 so that Y0i is 0 and Y1i is 1. And this would imply, because Z0 equals X0 plus Y0, this would imply that Z0i is 0 and Z1i is 1. So now you can fill the entries of this table and you get exactly this.
Yeah.
So this leads us to have the following definition. So we say that a Bowtie differs in the ith coordinate if X0i is different from X1i. So the choice of X was not important here. We could have also defined it as Y0i not equals Y1i or Z0i not equals Z1i. And what we showed was that if a Bowtie differs in the ith coordinate, then you can embed the GHZ distribution into the ith coordinate of the Bowtie distribution. So you look at the ith coordinate of the Bowtie distribution, it looks exactly like the GHZ distribution. In particular, when you sample inputs from the Bowtie distribution, the probability of winning the ith coordinate is at most 3/4, because this is exactly the GHZ distribution here. In particular, the ith coordinate is hard for the Bowtie distribution of P. So what have we done so far? We've introduced the concept of a Bowtie distribution. These are simple distributions, and we've shown how to pinpoint the hard coordinates of a Bowtie. These are exactly the coordinates on which the Bowtie differs. So this completes step 1 of the overview. Now we'll move on to step 2, where we're approximating P conditioned on E by a convex combination of Bowtie. So any questions up till now? Okay, so let's see how to do this. So here is what we want to do. You have a product event E with considerable measure. We want to show that P conditioned on E, the n-fold GHZ distribution conditioned on E, can be approximated by a convex combination of Bowtie distributions. Let's rephrase this question pictorially. Let's take the same graph I described a few slides ago. So here you have this complete bipartite graph. But now we're only going to consider the edges which are in E. So remember that the edges here are in one-to-one correspondence to the inputs to the n-fold GHZ game. And for every input that is in this event, we include that edge in G. So this event E defines a subset of inputs to all the players. For every such input, we look at the corresponding edge and we add it to our graph G. So this gives us a subgraph of the complete bipartite graph on 2 to the n by 2 to the n. Under the same correspondence between the edges and the inputs, the distribution P conditioned on E corresponds to the uniform distribution over edges in G. Furthermore, because the event has significant measure under P, it implies that this graph has many edges. More precisely, if your measure of the event under the GHZ distribution is at least some quantity n to the minus omega 1, then G has the same quantity, at least n to the minus omega 1 fraction of all possible edges. So if your event has good measure, then this graph is dense. Now, what we want to do, we want to approximate P conditioned on E by combinations of Bowtie distributions. So we want to approximate the uniform distribution on edges by convex combination over Bowtie distributions. So in this picture, for example, we're going to take either the blue Bowtie, the purple Bowtie, or the pink Bowtie with some probability and sample a random edge from the Bowtie. And we're going to show that this distribution of this edge is kind of the same as if you picked a random edge from this graph. So this is what we're trying to do. So let's see, how do we find Bowties and use this Bowtie approximation? So first I'm going to simplify the goal. I'm going to say we don't really need to find Bowties. We only need to find these objects. So the claim is whenever these edges are present, so you have these two blue edges and this green edge, then this edge must also be present. And in fact, it must be green. So here we are going to use the fact that it's a product event to simplify the problem of finding Bowties to finding these Z-shaped objects. And why can we do this? It's quite simple. So what does it mean for this edge to be present in the graph? It means x0, y0, z0 is in your event. In particular, it implies that x0 is in E1. What does it mean for this edge to be present? It means that x1, y1, z0 is in your event. In particular, it implies that y1 is in E2. Finally, this green edge implies that z1 is in E3. So putting all of this together, you conclude that x0, y1, z1 is in your event. So this edge must be present in your graph. And in particular, you can check that x0 plus y1 should equal z1. So what have we done? We have shown that because your edges come from product event, you don't really need to find Bowties. Sorry?
Just go back. The second line, do you mean x1, y1, z1 belongs to E? That's what you mean?
No, I mean x0, y1, z1. So yeah.
No, because you are assuming the blue belongs. No, that's x1, y1, z1.
Oh, sorry. I think you're right.
Because
yeah, I've repeated twice. Yeah, I think I meant x1. Thanks for the clarification. So this should be x1, y1, z0.
z0, yeah, right.
Yes. Yeah, thank you.
Okay.
Yeah. Yeah. So, okay, yeah. So what have we done? We have shown that because these edges come from a product event, it suffices to look for these objects, which are like part of a Bowtie. The other edge will necessarily be present if you find this object. So now the question is, how do we find such objects and approximate the uniform distribution over edges by such objects? Unfortunately, this is a hard question. So in general, if you're given a subgraph with a good density of edges, the question of whether you can find an object like this is difficult to answer because it has close connections with a combinatorial problem, namely the Rusa-Shemiridi problem. So here the question is, what is the maximum number of edges you can have in an n by n bipartite graph such that the edges can be partitioned into n induced matchings? So the connection is that if all of these matchings defined by a color, if it was an induced matching, then you would not have any cross edge going between the edges of the matching. So more precisely, if you look at, suppose your graph had fewer than these many edges, it could be that all of these matchings, this MZs, it could be that they're all induced matchings and they partition the edges. So this would mean that if you want to just use property about density, you had better get tight bounds on this RS number for graphs. But unfortunately, the best bounds on the Rusa-Semeridi number are kind of weak, in the sense the best bound is this. So using this, you could try to find bow ties and so on, but at the best, it would only imply that the value of g to the n is at most 2 to the minus omega log star n. So this is an extremely slowly growing function and definitely not inverse polynomial. So what this is saying is that you can't just use the fact that the graph is dense, and you're going to need to use stronger properties. So what we do is, so we will exploit this product structure more strongly. Additionally, we will use the assumption that the Fourier coefficients of the events E1, E2, E3 are small. So what our result will show is that for graphs built out of such events, actually the Rusa-Semeridi number is much smaller. So here is our main claim. We show that the Fourier coefficients, assume that the Fourier coefficients of E1, E2, E3 are at most delta in absolute value. Then the uniform distribution U over edges is close to the uniform distribution, close to the distribution of a uniformly random edge in a uniformly random bow tie. This is our main lemma. We show that sampling a random bow tie in the graph and sampling a random edge from the bow tie kind of induces the uniform distribution over all possible edges. So this is what we show. So any questions up to now?
What do you mean by Fourier coefficients of E1, E2, E3?
Just as sets. These are subsets of the hypercube, and
so you just take the indicator function and
indicator function, yes.
Can you say a bit about how does one justify this assumption? I mean, you would still want, yeah. Okay.
How do you make the Fourier coefficient? Yes, I'll come back to it.
Okay. Okay. Sure. Okay.
Okay. Yeah. Let's for now assume this and see. Okay. So let's see how to do this, and later I'll show how to remove this assumption. So, yeah. So let me give some intuition behind the proof of this. So the idea is going to be to bound the L2 norm of the distribution V. We're going to show that the L2 norm, or in other words, the collision probability of V, is close to 1 over the total number of edges in G. This is exactly the L2 norm in the uniform distribution case. So this would show that V and U are close in L2 norm. And by Cauchy-Schwarz, it would imply that V and U are close in L1 norm. So basically, it suffices to bound the L2 norm of V. And how do we do this? So let's look at what this distribution V does. It samples a random bow tie and a random edge in the bow tie. So the probability that you sample a particular edge is proportional to the number of bow ties containing that edge. So if you write on this distribution V as a vector, you would get exactly this. For each coordinate, for each edge E, you would sample the eth edge with probability proportional to the number of edges containing E, and you would normalize. There is some normalization factor. So to bound the L2 norm of this, we're going to bound the L2 norm of the numerator, and we're going to lower bound the denominator. So more precisely, we're going to show these two inequalities. The first one says that the denominator is large. That is, the total number of bow ties is large. The second equation is saying the L2 norm of the numerator is small. That is, the sum over edge of the square of the number of bow ties containing that edge is small. So intuitively, what these two equations do, well, if you have these two equations, you can divide one by the other and get this. But what is going on is that this first equation is saying that there are many bow ties. In particular, if you correct all the bow ties, they're going to kind of cover all the edges. The second equation is saying that a typical edge is not contained in too many bow ties. That is, this cover by bow ties is kind of a uniform cover of the edges. So the exact estimates that we get are that the total number of bow ties is at least 2 to the 3n times PE square. Now this is some inverse polynomial quantity, but 2 to the 3n is the total number of bow ties that are ever possible. So if your graph G was a complete bipartite graph, you would get 2 to the 3n. And this is saying you're not doing much worse. Similarly, for the second equation, 2 to the 4n is what you would get if your graph was a complete bipartite graph. And this is saying you're off by a factor of PE cube. So these two equations are the main technical part of our proof. So I'm not going to describe how to get these, but I will say that we're going to use Fourier analysis. In fact, I will show you what Fourier analysis lemma we use. So let's see where we use Fourier analysis. So we're going to make use of the following claim. So this says that if you have subsets ABC of f2 to the n, assume that the Fourier coefficients of C are at most delta in absolute value. Then the expected measure of A times B times C under the GHZ distribution is close to the measure of A times B times C under the uniform distribution. So the measure of the set A times B times C under the uniform distribution on X, Y, Z is exactly measure of A times measure of B times measure of C. And this is saying that as long as the Fourier coefficients of C are small, the measure under the GHZ distribution is close to the measure under the uniform distribution. So we're going to use this lemma, and we're also going to use a strengthening of this lemma, which I'm not going to describe. But for now, let's just look at this lemma. This is a really powerful lemma. So this allows you to estimate the measure of the event E under the GHZ distribution. So let's take our event E and assume that E1, E2, E3 all have small Fourier coefficients. If you apply this lemma, you can conclude that the measure of the event under the GHZ distribution is roughly the product of measures of E1, E2, and E3, which is what it would be in the uniform case. So this is allowing us to understand expectations under this highly correlated distribution by expectations under the highly uncorrelated distribution. So this is what is going to allow us to prove the estimates that I described before. The proof of this is also really simple. I'm not going to go into the details, but what's important here is that we use two facts. One is the convolution property of Fourier coefficients. So if you have the GHZ distribution, you have this nice property that the expectation is exactly this quantity, the sum of product of Fourier coefficients on the sets S. The first term here, which is the S equals empty set term, is going to correspond to the measure product of measures. For the rest of the terms, we're just going to use the bound on the Fourier coefficients of C. So because this term is at most delta, you can kind of take it out and you can basically bound the whole term by delta. So we're going to use this lemma, and so this is an expectation version of this lemma. We're also going to use a variance version of this lemma, and this is going to give us our estimates on the number of bow ties. So
roughly what this lemma is stating is the following. No? So I view the GHZ game is some hyperedge structure. It's a 3 uniform hyperedge structure on 0, 1, n. And it is sort of saying and then you're picking 3 sets A, B, C. And as long as one of the sets is more or less has 0, all its Fourier coefficients are low, then you're saying that this ABC, the picking of these 3, picking a random hyperedge is the same as picking independently. These hyperedges sort of mix well in this sense of the.
Exactly. So if you're looking at measure of product events under this picking of a random hyperedge, then as long as one of the events had small Fourier coefficients, then it's as though you were sampling a uniform 3 independent sets.
Okay.
Yeah.
So my question was, suppose you had some other distribution. Is this all that you use? Here is where you're using linearity crucially in the here. If I gave you some other game which had this property, that in which the hyperedges were the defining game and it had this property, would the rest of the proof just go through?
Yeah. So somewhere. Okay. So as long as you had like maybe we might use linearity in the sense we're going to like to talk about Fourier coefficients. It's easy when you have affine subspaces. So assume that your distribution was actually an affine subspace, and assume that you had this property and this lemma, and maybe a higher dimensional variant of it, in the sense you want this to hold even with the variance instead of expectation. then
Okay.
it would suffice. Yeah.
Okay. Okay.
In principle.
Okay. Okay.
Yeah. So, yeah. Okay.
Sorry, I have a sort of serious, stupid question. I don't know if I'm taking too much time from the, but I mean, if you
It's
feel this
good.
will
Very
take too
good.
much time, I
Yeah.
mean, like we'll take it offline. So the thing is, suppose I had picked these events as a random subset of a certain size or whatever. I mean, if I just take my restriction to be, I am looking at a random subset on the first player, random subset on the second player, random subset on the third player, then we are in the setup where all these Fourier coefficients are small, right? Of the corresponding events as sets, they will be small. In such situations, is it very easy to see that the bow ties will be of the right proportions? I mean,
that's a good question. I don't know how to see it apart from going through this whole property.
Proof.
That
Okay.
yeah.
Okay. Okay.
Sorry,
Okay.
if you pick a subset at random, I mean, why will the Fourier coefficient be small unless the subset is like big, right?
Yeah, any big subset, I guess.
So that already, okay.
So any large subset, I guess it would be small.
Yeah.
But even then, it's not easy to see. Like even a subset of size half, I don't see how to show that for the GHZ distribution, you can pick many bow ties. Yeah, I don't see how to show it without going through this.
I'll think about this.
Okay. Just so just time wise, Uma, so how much time will you?
I think I can finish in like 5 minutes.
Okay.
Yeah.
We started 5 minutes past this one. Okay.
Yeah. So yeah. So yeah, we can come back to the details again. But yeah, so let's yeah. So this is the Fourier analytic lemma that we use, and I'm not going to show you how to use this to derive these inequalities, but hopefully the main idea is that these lemmas allow you to treat the graph as though it was actually like treat the distribution as though it was actually the uniform distribution, in which case it's very easy to analyze these objects. So that's the idea. And so Ramprasad asked this question about how can you reduce the Fourier, how can you assume that the Fourier coefficients are small? I'm not going to define what the Fourier coefficients are, but Fourier coefficients being small is kind of the same as saying the maximum correlation with any hyperplane in F2 to the n is small. And the idea is that whenever you have high correlation, you partition the event. So whenever a set A has large correlation with some hyperplane, we divide the event, we divide the subset A into parts defined by this hyperplane, and we repeat on these two parts individually. We keep doing this until the maximum correlation with any hyperplane is small. And the idea is whenever you find some hyperplane with lots of correlation with A, it reveals a lot of information about the set A. And if your set originally had large measure, you will not be doing this too many times. So that's the idea. So as I've stated it, it looks like we use information, but no, not really. You can make these arguments without information theory. So this is saying that if your set is large enough, it cannot have too many large Fourier coefficients, so to speak. And so once you condition on these few Fourier coefficients, you'll be left with all Fourier coefficients which are small. Okay, so this says that, so this shows how to do the second step. So we take large product events E, we break them up into parts where in each part the Fourier coefficients are small. For any such event P conditioned on E, we approximate P conditioned on E by Bowtie distributions, and then finally we put all these Bowtie distributions together. Finally, I need to show you why these Bowtie distributions differ on a large fraction of coordinates. And I'm not going to do the details, but the proof kind of comes immediately from the fact that we proved that there are many Bowties. So if you look at this picture where you have all possible Bowties, and you look at the set of Bowties in G, we already showed that there are many Bowties in G. In particular, the set of Bowties in G occupy a polynomially large fraction of all possible Bowties. If you look at Bowties that differ in very few coordinates, that differ in less than 10% of the coordinates, they're going to be an exponentially small fraction of the universe. The reason is because if you pick a typical x0, x1, where x0 is not equal to x1, they're going to differ in like 50% of the coordinates. So the probability that they differ in less than 10% of the coordinates is exponentially small. So this implies that these bad bow ties are an exponentially small fraction of the universe. The number of bow ties in G is a polynomially large fraction of the universe. So in particular, if you look at the bad bow ties in G, they form an exponentially small fraction of the bow ties in G. So this is saying that a typical bow tie in G is going to differ on a significant fraction of the coordinates. So this completes the third point in the proof overview. So just to quickly recap, what did we do? We introduced the concept of bow tie distribution. We then took large events E and broke them up into parts where the Fourier coefficients are small. We showed the desired approximation by bow tie distributions for each of these parts and put them together. And finally, we showed that most of the bow ties in this distribution are hard on a significant fraction of the coordinates. So putting all this together, we have the claim. So let me conclude my talk.
Okay, sorry, just one question.
Yeah.
So suppose if the goal was to instead show that the value of the claim is, say, inverse quasi-polynomial, like 2 to the polylog or something, where did we really use the fact that you only had a poly?
Good question. So there are two parts where we use inverse polynomial. So one is in this final part where we're conditioning on Fourier coefficients. For some technical reason, if you are handling each of these sets independently, then putting them all together, you incur a factor of inverse polynomial. But more importantly, to have this equation, so imagine that A, B, C are now inverse polynomially large. The problem is this delta, you cannot make it any smaller than 1 over square root n. So you cannot make the Fourier coefficient smaller than something like 1 over square root n. So it had better be that these sets are themselves like at least polynomially large, otherwise this error term will dominate. So that's a good question, yeah.
Okay, yeah.
Okay. So right, so let me conclude the talk. So our talk, in this work, we show that the GHZ game has the parallel repetition value of the n-fold GHZ game is at most n to the minus omega 1. And we presented a new proof of this, which we believe to be simpler and more direct. So this concludes my talk. Any questions? We can go back to the details if necessary.
Questions? Let's thank Umar. Any questions?
I had a question, but I'm not sure if you can hear me.
Yeah, we can hear you.
Okay, good. so probably a stupid question, but so this was like this was a case where all the allowed inputs were at Hamming distance 2 from each other. So is there some generation of that kind of the DH, the Dinur, Harsha, Yuen kind of?
That's a good question. So as far as I know, you really need the fact that they differ on exactly, well, yeah, actually maybe Prahlad can answer this if.
Okay, so what was your question? Actually, we do define this notion of K-connected games, where the K-connected is on how many things you have to flip in order to.
So this is 2 connected in that sense.
This is a 2 connected thing. A 2 connected thing, but all the current proofs require you to be, actually we call it K-1 connected, or I don't know whether it's K-1 connected, yeah, whatever. In the case of 3 is both of them are the same. But all what does DHVY prove? DHVY in that paper, what we show is the existing. Basically, we ask the question: when can we extend the proofs in the 2-player games to the K-player games? And we were able to show that if the graph were 1 connected in this way, these sort of proofs can be lifted there. But once the graph becomes anything weaker connected, like 2 connected, the proofs don't seem to. Somehow you need to show this sort of this. There's this Raz's trick, which Raz attributes to Razborough, you need to do this sort of sampling, hide the coordinate, this sampling. You needed some mixing properties of the underlying game. And you needed this one connectedness to do it. Notice that one connectedness is obviously true for a two-player game. Otherwise, the graph just becomes two. You're running it on completely disjoint parts, and you can think of the game going parallel and so on. So, seems to use this fact effectively. I don't know how to extend the proof, or you have to come up with a very different style of proving, which is what both these proofs do to prove the.
So the alphabet is always binary in all of these.
Yes, yes.
Yeah, if the answers could be any finite alphabet and it would still work. The questions though are just
questions.
Yeah.
Your proof doesn't depend on what the predicate or what the answers are.
Yeah, but the questions have to be. The connectivity for that, it probably matters because it could probably hide.
You could define connectivity on another like general. So there you would ask that you can. Yeah, again, it would be the same definition that you can flip any one coordinate and connected to that question. So we're actually working on that, and so we're able to show it for a relaxation of this. So we have not yet published this, but I think we're able to show that as long as the projection onto the players is connected. So if you look at the graph on just the kth input, and if you look at the projection of this graph onto that player, as long as that is connected, it suffices. So in other words, for every two inputs x1 and x1 prime, there exists a x2 to xk such that both x1 up till xk and x1 prime, x2 up till xk are valid in your support. So it is possible to generalize this a bit. Yeah.
So this is true for GHZ because
it's not.
No, it's not true.
It's not true. Yeah.
Oh, okay.
You can't fix all the other coordinates and just change one coordinate.
Yeah, because there are two ones always.
Yes. So the GHZ is still a different class of games.
So, just a question about. So in this case, you could do away with information theory. So is there a meta theorem about situations when information theory can be thrown away?
I doubt it.
But in some sense, the Dinur-Stoider proof is information theory free, no?
Maybe, yeah. I think that proof and is pretty much the only other one I know. Yeah, even the previous proof actually used information theory, but in a very light way. Like they basically, the information theory argument I showed to reduce the Fourier coefficients, that's where they use it. But that really doesn't need information theory. So maybe even the previous proof, you can say it without information theory. So yeah.
Any other question? Any further questions? If not, let's thank Uma again. Yeah, thanks.